All right, well, good morning, good afternoon, or good evening, everyone, and welcome either back or for the first time to the point distribution webinar. Today, we have my academic sibling, Michelle Mastrianni, from the University of Minnesota, giving a talk about the bounds for star discrepancy with dependence on the dimension. So, Michelle, take it away.
Thank you. Thanks to the organizers of this webinar. This has been a really nice webinar. I've learned a lot from it, so I'm happy to be speaking today. So yeah, I'm a graduate student of the at the University of Minnesota, and I'll be speaking about bounds for star discrepancy with dependence on the dimension. So this will mostly be a survey talk. I'll give some introduction and background, including introducing the concept of Vapnik-Cervonenkis classes, and discussed how they're used in one of the upper bound proofs by Heinrich, Novak, Wasilkowski, and Wozniakowski, and then talk about Aistleitner's more direct upper bound proof that makes use of some similar ideas, but kind of avoids using VC classes and more directly uses the geometry of the space. And then at the end, I'll touch on a lower bound result as well. Okay, so first, some notation so that we're all on the same page. And in case you haven't seen discrepancy before, which some of my friends who nicely came to this talk have not probably. For those who aren't familiar with discrepancy, we measure the star discrepancy, which I'll get to on the next slide, of a point set P in the d-dimensional unit cube with respect to some class of sets. And the idea is that the class of sets should be complex enough so that the discrepancy gives some sort of measure of how well distributed the point set is in the d-dimensional unit cube. So before just defining the star discrepancy over the whole class of sets, we need a definition of local discrepancy for a single set in the class. And the local discrepancy is essentially given by the difference between the expected proportion of points that fall in the set, which is given by the Lebesgue measure, again, since we're in the unit cube, minus the actual proportion of points that fall in the set. So this is the normalized version of discrepancy, may be used to the unnormalized version, but I'll be using the normalized version throughout the talk, and it'll affect how the bounds are written and stuff. So this talk focuses on discrepancy with respect to the set of corners or boxes anchored at the origin in the unit cube. So the corner given by a point X would be just, an R2. This is your corner C sub X as it's defined there. Oops. So we need a definition of discrepancy with respect to the entire class of sets. And to do that, we take a supremum over the absolute values of the local discrepancies for each corner. So for a point set P, it asks essentially what is the worst possible deviation between the expected proportion of points in a corner and the actual proportion of points. And then what we're interested in and what we're finding bounds on in this talk is the so-called minimal star discrepancy of point sets in the d-dimensional unit cube. And it's a function of the number of points and the dimension. It takes an infimum over all point sets with size n of the star discrepancy for that size, or of the star discrepancy for the individual point sets. So in some sense, it asks for the star discrepancy of the most well-distributed point set, whatever that means. And many of the discrepancy results can be stated in terms of the inverse discrepancy, which asks kind of the opposite question. So what is the minimum number of points with discrepancy at most epsilon? And that's a function of the dimension and epsilon. Okay, so as I mentioned in this talk, we're going to be searching for bounds based on the dimension. So the asymptotic behavior of the star discrepancy of the class of corners is of order at most 1 over n log of n to the d minus 1. So this is good in terms of the number of points, but it ends up not being very useful if you're concerned with high or discrepancy in high dimensions, particularly for certain, and also the constants here are also dependent on or exponential in the dimension. And there are known point sets that achieve this bound. So like the Halton-Hammersley set in dimension D. But for certain applications, and this is an interesting theoretical problem as well, because it turns out that the proofs here have sort of a different flavor when you're trying to search for bounds based on the dimension. They have sort of a different flavor from typical discrepancy proofs. But also in applications, there are certain applications where this might be of interest. So you might have, for example, in finance, you might end up with a needing to integrate a function of 360 variables if you have 30 years worth of data that's measured in months. And high dimensional integration makes use of low discrepancy point sets using quasi-Monte Carlo methods, in which a random point set is replaced with a deterministic construction with low discrepancy. So discrepancy is useful to sort of high dimensional integration problems. And the usual discrepancy bounds wouldn't be of any help here because this is increasing in the dimension for n less than e to the d minus 1, which in practice is prohibitively large. So that's sort of some motivation for why we might want to search for discrepancy bounds with respect to the dimension, besides the fact that it's just an interesting theoretical problem. Okay, so central to the discrepancy proofs will be the concept of Vapnik-Cervonenkis classes, or VC classes, and VC dimension. And if you get nothing else out of this talk, I think you should hopefully get this definition or concept out of it. So the VC dimension gives some measure of richness or complexity of the set, or of the class of sets. And there are a lot of known inequalities and results involving VC classes. So let's turn to the definition. So a family F of measurable subsets of some set X. By the way, I'll be referring to different types of subsets. So if I'm referring to a finite set, a point set with finite cardinality, I'll make sure to call it a point set or a point subset. But a family of just any subsets of X is a VC class if there's a non-negative integer V such that this inequality holds for any point subset with cardinality V plus 1. So on the right-hand side, you'll notice that this is the total number of subsets of a point set of size V plus 1. And this is strict inequality here. So what this is saying is once you get up to dimension or cardinality V plus 1, it's impossible to pick out every subset of your point set with elements in your VC class. So there's no point set of size V plus 1 such that you can pick out every single subset of that point set with elements in your VC class. Note that if the dimension is V, you only need to find one point set of size V that is so-called shattered. So I'll get to that in a second. Shattered meaning all the subsets are picked out by the VC class. So yeah, so I'll be using this word a bit, shattering. And so the VC class is said to shatter a point set if it picks out all the subsets of the set. All right. So I want to do a couple examples of the VC dimension just to give you a flavor of some sort of natural classes of sets and their VC dimension. So first, consider semi-infinite intervals on the real line. So all intervals of the form like minus infinity up to t. So this class has VC dimension 1. And to see that no 2-point set can be shattered, if you have something like this, you can't get the singleton set B because you can't pick out B with one of these intervals without also picking out A. For closed intervals on the real line, you have sort of a similar issue. So you can't pick out, so this one, B can't be picked out. And for this example, this single or the set A with containing just A and C can't be picked out. because you'd have to also pick out B as well. The set of corners in RD, so this has VC dimension D, and I'm going to go through this because the set of corners is the class that we're concerned with in these discrepancy proofs. So to see that a D point, there exists a D point set that can be shattered, you just take this set essentially, and then you can shatter any subset by just taking the corner with ones in the corresponding locations. And then for to see that a D+1, there's no D+1 point set that can be shattered by corners. You take the subset of at most D points, which are maximal in some coordinate, and then this subset can't be picked out without picking up other points. So in R2, for example, you might have a situation like this. Each of these is maximal in one of the coordinates, and any corner that picks out both of those has to pick out the other point as well. Of course, that's just one configuration, but that, yeah, generalizes. Okay, so a few more examples. So for half spaces in RD, in R2, for example, 4 points can't be shattered by closed half planes. Either one of the points is contained in the convex hull of the others, and then you can't pick out the outside points. Or you have some affinely independent set, and then the opposite points are a problem. So you can't pick out only the blue points or only the orange points there. For axis parallel boxes in RD, the VC dimension is 2D, twice the dimension. So in R2, for example, you could take the set of points that are either maximal or minimal in some coordinate, and there are at most 4 in R2, and any class that picks up these points must also pick up others. So take set of points, max or min in some coordinate, and that's a problem. For disks, you might have some situation like this with opposite points. And then if you have disks picking out, so you couldn't have this situation because any 2 disks can intersect in at most 2 points. So this is a problem. One of those opposite pairs can't be realizable without picking out the other opposite pair. Balls in RD, I just wanted to state that, but this is due to Dudley 79. And then convex sets. So this is an example of not a VC class because it has infinite VC dimension. So to see this for any integer n, just take an n point set lying on the circle. And you can pick out any subset that you want by just taking the convex hull. So if you want to pick out that subset, you just take the convex hull. So this is independent of n. So you have VC dimension infinity. So that's much more of a complex set in a sense. Okay, so after you learn about the definition of VC classes, sort of the next thing that you learn is about this important inequality. So we can ask the question, if you have a VC class of dimension V, given a point set A of cardinality n, so in everything I say, I'll be assuming this, how many sets at most can be picked out by your VC class? So we know already that if n, the number of points, is less than v, less than or equal to the VC dimension v, then 2 to the v subsets can be picked out. All of them can be picked out. But what happens once our number is much larger than the VC dimension? So this lemma gives an answer, and it is essentially polynomial in n, the size of the set, with the power being the VC dimension. So for VC classes, the maximum number of subsets that can be picked out gets very small relative to the total number of subsets because you have polynomial versus exponential growth. And the proof of this lemma uses induction on n plus v, so I'll just briefly talk through it. We'll go through it in detail. But in the induction step, we construct two new classes out of our class F by fixing any point x, element x, and considering the class that consists of all sets that contain x and all sets that do not contain, and then the class of all sets that do not contain x. And the class of all sets that contain x, you can argue that has VC dimension at most v minus 1 and acts on n minus 1 elements, or you can show that acting on all elements not including x is the same as acting on all of the elements. And for the first set, the class of sets that do contain x, that acts on n minus 1 elements as well, and you can argue it has VC dimension at most v. So by induction, by our induction hypothesis, we basically have for one of the classes that the number of sets picked out is less than or equal to this sum. And then for the other class, we have, so I'm trying to bound the number of sets picked out by F. So I'm adding, because these are disjoint classes, adding based on our induction hypothesis, the two, the bounds for the two individual classes. And then you can rewrite the second sum as basically just going from 1 to v, and then of n minus 1, choose I minus 1. And then by just a Pascal's triangle identity, this is equal to sum from 0 to v of n choose I. Or you might have an extra +1 in there because of the differences in the sum index, but yeah. So I'll just put this bound to be safe. So that's essentially kind of the flavor of that proof. Another concept before I turn to the discrepancy proofs, well, there are a few more slides actually, but another important concept that will be of use here is covering numbers, which are sort of intimately related to VC classes. So the covering number with respect to epsilon of some metric space equipped with a distance metric is the smallest number of closed epsilon balls that cover the space. So let me just go through a couple examples of this. You might have a cover of the unit square with the normal L2 distance. So if this is your cover, then for any point here, we should be able to find some point in the cover such that these 2 points are distance less than, so this is a 1/4 cover in this picture. So this distance has to be less than 1/4. So for any point in your space, you can find a point in the cover that's less than or equal to than 1/4 from it. Another example, you could take a different distance metric than just the usual ones. So maybe you take the metric given by the symmetric difference of the corners defined by 2 points. So for example, and this is a 1/4 cover as well, it doesn't look too much different from the other one. So it's possible that but like that this one is also an L2 cover and the previous one is also a symmetric difference cover, but I tried to make sure that these were in fact covers with respect to the different distance metrics. So for this one, you would want to find for a given point, you would want to find a point, or you would be able to find a point in your cover such that the if you take the difference between the corner, the Lebesgue measure of the corner defined at your point and the corner defined at the point in the cover that's closest to it. So I'll just call that CP. The Lebesgue measure of the symmetric difference should be less than or equal to 1/4 here. So, and in this cover, we didn't, so you'll see something similar to this later in a proof, in Aistleitner's proof. I'm going to come back to this example. And in that case, I'm going to impose an extra condition that each of the points has to be lie between, coordinate-wise between 2 points in the cover. So here I didn't impose that condition, but you could also impose that extra condition for the cover. Okay. So we're almost to the theorem statements, the discrepancy theorems. But I want to say one more thing before getting to those. So I want to say a few words on why VC classes are somewhat natural classes of sets with which to study discrepancy. So to begin with, you can find rich enough VC classes with which to obtain some measure of well-distributedness. For example, corners or axis parallel rectangles, but VC classes still have relatively low complexity. And the Sauer-Schalat lemma hints at this because for a point set of size n, for n large, the number of sets picked out as a proportion of total sets is very small. So intuitively, there must be a lot of similar sets in the class in some sense, which behave similarly with respect to discrepancy. So similar sets. And as discussed, VC classes have known geometric properties such as connections with covering and packing numbers. I don't know if I said this, but the VC dimension can be used to prove bounds on covering and packing numbers, or has been used in several of those bounds. And there are also even more direct implications for the so-called combinatorial discrepancy, which I won't define here, but it's a more discrete measure of discrepancy. It deals with set systems and balancing red-blue colorings of a point set such that each set in your class of sets is colored as evenly as possible. So for example, finite VC dimension characterizes set systems for which the combinatorial discrepancy is on the order of, so finite VC dimension, combinatorial discrepancy is on the order of at most n to the -1/2 square root log of n. And for infinite VC dimension, you have O of 1. So you can see that the infinite VC dimension, which are much more complex sets, give worse discrepancy bounds in the number of points, which makes sense because you're measuring, you're sort of taking not even more sets, but in some sense you are taking, you know, a supremum over even more sets, whatever that means. Okay, so let's finally turn to the theorems here. So stated here are 2 upper bounds for discrepancy based on the dimension proven by Heinrich, Novak, Wasilkowski, and Wozniakowski in 2001. And the difference here is that this first theorem has an extra factor of square root of log dn. So this first theorem is proven pretty directly using basic features of empirical process theory, and I'm going to talk through that in some detail just so that you get a flavor of these proofs and how these proofs work. And then this next theorem gives an improvement, so you don't have that extra square root of log dn factor, but it makes use of sort of a black box VC inequality proven by Talagrand. It makes use of the fact that the set of corners is a VC class. And so the actual VC inequality is very difficult to prove, but I'll give some sort of sketch of that proof as well. So before we get to the proofs, I just want to remind you of two inequalities for IID random variables with mean 0 and absolute value less than or equal to 1. So Hooftings versus Bernstein's inequality are given here. And you can see that Bernstein's inequality depends on the variance. So intuitively, this should give good bounds for random variables with low variance. And the proofs we see are probabilistic in nature. They're not constructive, but they just show the existence of some point set. So they consider discrepancy of random point sets in the unit cube, and then via probabilistic arguments show existence of some point set satisfying the desired discrepancy bound. And so it makes sense that we might want to use these inequalities on the random variables because we're going to essentially have random variables given by what you saw in kind of the definition of local discrepancy, where these are random variables representing points. So this takes, like, for a given corner, it takes the expected number or expected proportion of points that fall in the corner minus the actual proportion of points given by these random variables that fall in the corners. So this clearly has mean 0 and absolute value less than or equal to 1. So it makes sense that we would be applying these inequalities. All right, so for the weaker upper bound, first I'll just go through this. So essentially the idea here is to replace the class of corners by a finite set for approximation purposes. And then we can replace the supremum in the definition of the star discrepancy with a maximum over the finite set of the local discrepancies given by each corner in this, given by points in the approximation. And that approximation, then you have a possible decrease of the star discrepancy by delta. So you sacrifice that via this approximation. And then we take IID uniform random variables and we take these differences as I showed on the previous slide. So that kind of represents the local discrepancy for a given corner. And then via Hooftings inequality, we can bound the probability that each of these random variables is greater than or equal to delta by this. So we can use for our star discrepancy, use the finite approximation to bound the probability that the star discrepancy is less than or equal to 2 delta below by the probability that the maximum over the finite point set of these local discrepancies is less than or equal to delta. And then just rewrite this in that form. And then you can take a union bound here. So this is the union bound because we just want one of these point sets to have local discrepancy larger than delta here. So this gives a union bound where this is the maximum number of points, or like an upper bound for the number of points given by the approximation that was on the previous slide. And I didn't quite say this, but we're approximating with a finite or with an equidistant grid. So we're taking kind of a crude partition here where everything is equidistant. But m plus 1 to the d is the upper bound on the number of points in that approximation. And this is strictly positive for delta greater than delta naught. So if you play around with everything, you get this equality for delta naught squared. And so then you can conclude that for any delta greater than delta naught, there are points. So we've now essentially proven that our probability is strictly positive. So the probability that the discrepancy or the local discrepancies for each corner given by points in your finite approximation is less than the desired bound is strictly positive. That means there must exist a realization that gives you star discrepancy less than or equal to 2 delta, again, using our passing from the finite approximation to the star discrepancy. And so since this is true for all delta greater than delta naught, we have this, and the proof is complete. All right. So now let's turn to the stronger upper bound proven by Heinrich, Novak, Walzakowski, and Wozniakowski. I'll show in a minute how this bound follows easily from the VC inequality given here. So the way I've written it here, this is sort of the black box VC inequality that we're going to use. And the way I've written here is the way it's written in their paper, but in Talagrand's paper, it's actually even more general and not just for VC classes. So you'll see that in a minute as well. But essentially the condition imposed on the class of sets by Talagrand, which has to do with the covering number, is automatically satisfied by all VC classes. And so you can restate it in terms of VC classes. So the idea here is to optimize the right-hand side with respect to S such that this probability is strictly less than 1. Because then this is taking, the probability that the supremum over this set of the local discrepancies is greater than or equal to S times n to the -1/2. So if we optimize if we optimize the right-hand side in terms of S, where S will depend on the dimension, which is also the VC dimension in this case, since the class of corners has VC dimension D, we can make this probability strictly less than 1 and then obtain a realization that satisfies the discrepancy being less than this desired bound. So note that the Gaussian tail appears here, and in fact, Talagrand's result starts with the Gaussian case, and it's easier to prove there. So I'll discuss that in a minute. So first, I just want to discuss how the discrepancy bound follows from this VC inequality. So I've copied the VC inequality up here. You need a countable class, so you just approximate the set of corners by the set of corners given by rational points. This doesn't change very much. And then this is the S that will sort of optimize the right-hand side. So it's in terms of the VC dimension. And again, that's D here. So we get our desired D to the 1/2 factor. So, and then you choose lambda naught such that this holds. And then for lambda bigger than the max of these values, the right-hand side of the VC inequality above is strictly smaller than 1. Because if you replace S, I'll try to do this here. If you replace S with your chosen S there in the right-hand side, you get 1 over lambda VC to the 1/2 times K lambda squared VC for VC. And then this is equal to this. And then we've chosen delta naught such that this thing holds. So you can basically replace this piece with e to the 2 lambda squared VC. And then you have e to the 2 minus lambda squared VC. So this is less than or equal to 1 over lambda VC to the 1/2, which is less than 1. Sorry, got a little crowded. So then you have something that's strictly less than 1, which ensures the existence of a point set with star discrepancy less than our desired bound. Okay. So as I've said, sort of the difficult thing here is the actual proof of that VC inequality. So I want to kind of go through that briefly. So it's stated in Talagrand as follows. Again, it's not stated in Talagrand in terms of VC classes, only this covering number condition. And it's a result of Hausler that covering number condition is always satisfied by VC classes. And note that the covering number condition here assumes that the metric is that probability of the symmetric difference between two elements in your VC class. Okay. So the idea is first to study Gaussian processes where the result follows a bit more simply because it's easier to control the expectation of the supremum here. So first we break the index set. So you can think of the index set as your like class of sets. And you break the index set into pieces each with similar diameter. And you can control the tails of the supremum by controlling the expectation of the supremum. But then we have this sort of bound on these probabilities, these tail probabilities of the supremum that depend on both the expectation, but also the number of pieces of your partition. So you need to control both at the same time. And bounding the expectation of the supremum involves integrating an expression involving the covering number on an interval the size of the diameter. So we have to take the diameter sufficiently small so that the expectation is controlled, but then the number of pieces of your partition becomes too large. But there's this sort of idea or overarching idea here that the main contribution to the supremum should come from the variable where the variance is maximal. And with this idea, we can take a nicer, essentially dyadic partition. Here, the base is 4 rather than 2, but it doesn't really matter. So we take an essentially dyadic partition. So partition the sets, the index set into sets of different dyadic orders and use what's called a dyadic chaining argument on each set in your class of sets. And remember, the set of sets are essentially sets of indices. So then you can partition those into a few random variables with large variance and many with small variance, and control the expectation better on those with small variance. So that was for the Gaussian process case. For the general case, you use the same partitioning scheme. So, and then the bound on these probabilities look a bit different. They're a bit more complicated than in the Gaussian case, but they still require controlling this expectation. So again, for indices whose corresponding random variables have small variance, it's easy via Bernstein's inequality to control the tails and get a good bound on this expectation. And then you can bound the cardinality on the set of remaining random variables which have large variance so that its contribution is controlled. Okay. So in 2011, Aistleitner was able to give a much more direct proof of this upper bound that bypasses the VC inequality thing, inequality, and computes an explicit constant here. So no constants were computed in Talagrand's paper or the Heinrich, Novak, Wazakowski, Wozniakowski paper. So here you're going to approximate the set of corners with a finite set, just as we did in the weaker upper bound proof. So roughly n to the d over 2 sampling points are needed. That was the case in the weaker upper bound proof. If you sacrifice much more than that, you sacrifice some of the discrepancy. And then use a direct dyadic partitioning argument rather than the black box of the VC inequality, as I said. So we're going to express the indicator function for each corner as a sum of indicator functions for a few sets with large variance and many with small variance, and then use Bernstein's inequality rather than Hoofding on the many variables with small variance, which leads to an improvement in the bound. So as a sketch of this proof, we're going to use Gnewuk's bounds on covering and bracketing numbers. So bracketing is a more restricted notion of covering where you have a finite set of pairs of points, such that this is sort of the symmetric difference distance metric. So the difference between the Lebesgue measures of 2 points in your pair has to be less than or equal to epsilon. And each point in your unit cube has to be coordinate wise between the points in one of the pairs. So, And so it's a little bit different because it concerns pairs of points rather than a set of points as a normal cover would. And then these are Genewig's bounds on covering and bracketing numbers. So this is the usual covering number. And then this is the bracketing number defined analogously. Okay. So to sketch this proof, in dimensions 1 and 2, the theorem is clear because we're well versed in those dimensions. We have known examples like the van der Corput set, for example. So we assume D is greater than or equal to 3. And then that assumption is just to kind of, for the purposes of computing the constants. Then we let big K equal to this. This is sort of, so 2 to the minus K is the smallest size interval that we'll consider in our kind of dyadic partition here. And this big K was chosen so that you get the number of approximating points that you need. Then for little k between 1 and big K minus 1, you construct 2 to the minus K covers, so regular covers, that satisfy the Genewig covering bound. And then for the big K, you construct a bracketing cover that satisfies the Genewig bracketing bound. And so I have a picture here of what happens in one dimension, even though we're not technically concerned with that in the proof. So for a given point, this is our corner defined by that point. And essentially we find 2 points, or a pair of points rather, in the bracketing cover. So this is a pair of points coming from the bracketing cover such that this point lies between them. Then for the smaller of those 2 points, so this one, you approximate, you find a point in your 2 to the minus 3 cover. So here I assumed K was equal to 4, such that these 2 points are distance 2 to the minus 3 from each other, or less than or equal to 2 to the minus 3. Then you approximate this point with something in the 1/4 cover. So you have this, and so on. So essentially what we've done here is partition the corner into sets where we know something about the Lebesgue measure of those sets. So let's do this in dimension 2, just for another example. So let's say that we pick this point here, and then we have the corner defined C sub x. Also, as I said before, when I was going over covering numbers with the symmetric difference distance, that's what we're doing here, but we're also imposing the other condition that the each point has to be coordinate-wise between 2 points in your cover for this example. So I didn't put like a bracketing cover here because it's kind of difficult to visualize pairs of points, but assume that this point X is between 2 points in your bracketing cover. And then you approximate, so like maybe this is the point in your bracketing cover. And then you approximate that point by the, so here the blue points are a 1/8 cover, the green points are a 1/4 cover, and the orange points are a 1/2 cover. So then you approximate this point. So maybe I'll call this corner C sub B for bracketing. Then you approximate that by something in your 1/8 cover. So I'll call that C sub 3 because it's 2 to the minus 3. And then you approximate this blue point by something in your 1/4 cover. So make that green point right there. So that's C sub 2. And then you approximate that by something in your 1/2 cover. So C sub 1. So now we know that basically we know something about the sizes of these, the differences between these things. So C sub x minus C sub b is less than or equal to 1/16 if that was a 2 to the minus 4 bracketing cover. C sub 3 minus C sub 2 is less than or equal to 1/8. And C sub 2 minus C sub 1 is less than or equal to 1/4, and so on. Okay. And then we know that the number of points in the 1/8 cover satisfies that Ganewu covering bound, and so on and so forth for the other covers. So if you take the set of all sets of this form, you can approximate that by the number of points in your cover here. So again, that satisfies the Ganewu covering bound. And then A sub big K would be the set of all sets of, if you go back to here, like this form, C sub X minus C sub B. And that satisfies this covering bound. And then you take IID uniformly distributed random variables on the unit d-dimensional cube, and you can use Bernstein's inequality to bound the probability that the local discrepancies are greater than or equal to some number t, which will be our desired bound, for all intervals in the set of all sets of this form. So we're essentially taking all intervals of size at most 2 to the minus k and considering those together, the local discrepancy of those together. And then we write B sub k to be, again, the union over intervals in the set of all sets of which have Lebesgue measure less than or equal to 2 to the minus k, and consider the probability that one of them has local discrepancy larger than what we want. Then we can choose constants appropriately so that these probabilities for sort of the intervals with larger variance are less than or equal to 1/4. And for the intervals with smaller variance, we use Bernstein's inequality, as I said, and choose constants so that each of these satisfies this. So then when we add them up, we get a probability strictly less than 1, which ensures the realization of a point set that satisfies basically that none of the local discrepancies for the individual intervals in all of the sizes that we've considered, or sets of different sizes that we've considered, has discrepancy larger than what we want. Then we can use those estimates to pass to the discrepancy for all corners, and use the estimates from these individual pieces to compute the final constant, which is 9.65. So I'm running out of time. I wanted to get to the lower bound proof. But there have been several improvements on the constant. So Possing and Weiss in 2018 used Aistleitner's method pretty much exactly, combined with an improvement on the covering numbers to improve this slightly to 9. There have been a couple other improvements along the way by Dorr and then Ganewuk and Hebbinghaus. And then Possing and Weiss this year, again, used a further improvement on the bound for bracketing covers to show that you can further improve the constant to roughly 2.5. And I learned about this at the Burrs conference where Hendrik Possing gave a talk a few weeks ago. So that's how I became aware of these improvements. Let me just really briefly touch on the lower bound result. So this is by Heinrichs, and you can obtain essentially a lower bound result that's polynomial in D over N. And this makes use of the VC dimension as well, including the Sauer-Schalat lemma and bounds on covering numbers. There's also a theorem of Dorr that gives a lower bound on the expected star discrepancy, which is square root of D over N. So that's kind of interesting. So I'll skip this, but one of the major open problems here is to close the gap. So we've just shown this upper bound, and then this is the lower bound given by Heinrichs. So one of the major results or open problems in this field is to close that gap. And then also find points that satisfy the stronger upper bound constructively, which would be more useful for problems involving high dimensional integration with quasi-Monte Carlo methods, because we know that there are point sets that satisfy this desired discrepancy bound based on the probabilistic proofs, but we don't actually have like a constructive set that you could use in practice. Okay, so that's essentially all I have, and I have a couple slides of literature if you want to peruse that.
All right. Well, yeah, thank you for the great talk, Michelle. Before I open the floor for questions, I realized I forgot to say this at the beginning. A reminder to everyone that after we have questions, there will be time afterwards for just socialization or further mathematical discussions. So please, feel free to stay on afterwards. But now, do we have any questions for the speaker?
Yeah, I think I have one or two questions. On the previous slide, you said like an open problem is to close this gap between the lower bound and the upper bound. Do you know if one of them is expected to be sort of true, like asymptotic, like, because there's a difference there, the square root or the just d over n. Do you know if like one of them is expected to be true? Like,
yeah, I don't know. I mean, I think the fact that there's this result on the expected star discrepancy, that's square root d over n, maybe suggests that that is the true. Yeah, and I think that's been conjectured that this is probably, I don't know, someone can correct me.
That makes sense. Yeah.
Yeah.
Okay.
Yeah.
Yeah. Thank you.
Yeah.
Other questions for the speaker? Well, I had a question about a slide that, let's see. So hang on, there's something in the chat, but the bound for the expected star discrepancy is only for Monte Carlo points.
Oh yeah, that's true. Yeah, that's for, so that, yeah, I kind of was going fast at the end, but this is for random point sets. So yeah, that's a good point.
Okay. The question that I had, so is it back a couple of slides where you were showing improvements on the bounds that have happened in the last few years, and so right, the two by passing and Weiss, those were talking about using improvement on the bound for bracketing covers. For the other two improvements, that happened that are in between, do you know, did those use similar methods, or did they somehow make improvements in different ways?
Yeah, I'm kind of curious. These are actually both preprints, so I wasn't, and they're not on archive, I think, so I wasn't.
Oh, even the one from 2016?
Yeah, or one of them. Yeah, I don't think I was able to find either one actually. So yeah, I don't have a good answer for you there, but I'm also curious about that.
Okay.
So it seems that both Aistleitner and this proof of VC inequality by Talagrand, they both use some sort of binary partition, right? At the same time, you said that the constants in Talagrand in the VC inequality, that constant was not explicit, right? But then in Aistleitner method gives an explicit constant. So I'm curious, could you do something like apply Aistleitner's method to the VC inequality to get the explicit constant there? It seems so. The underlying construction, right? It seems more or less the same, or that was just my impression. I don't know.
Yeah.
Anything, but again, the binary partition is just was in. Okay, so maybe let me phrase it like so. So was Aistleitner's method just making explicit well, one of the things was making explicit some elements of the construction related to this partition. So could you do the same for VC inequality?
Yeah, I think the constants could be computed for the VC inequality proof. Because it's like a very long paper, there's a lot of, things that need to be proven to get up to this result. So I think he might even say in the paper, like, I'm not computing constants here, but you could theoretically compute constants. And then the VC inequality proof would actually, because like Aistleitner's proof is more direct, so it's nicer to read, and you can tell what's going on more with this dyadic chaining stuff. But the VC inequality proof could be more general in the sense that you could potentially get discrepancy bounds for other classes of sets. So that's kind of what's nice about that one. But then, yeah, the constants are not explicitly computed there, but I think you could compute them.
Right, you're exactly right. So Talagrand does say that the values of the constants provided by our proof would already not be outrageous. So if you apply Talagrand, that's not outrageous constants. So that's good. So you can, in principle, just read that. Okay, thank you.
Other questions for the speaker? All right, well, just in case, I'm going to stop the recording now.